Welcome back to our SPSS regression series. In this series, we're going to be focusing on things like residuals and distances for outliers and whether or not they're influential. We're going to be doing this statistically. So we're going to look at things that we've done in class, such as studentized residuals. And instead of looking at standardized residuals or just the error divided by its variance, here we modify that just slightly so that it takes on a t-distribution, but effectively, if it helps you, you can think about them just as standardized residuals, but we're going to use studentized residuals instead. We're going to look at some distances. We'll focus in on Cook's D and leverage points that we've focused in on in class. These will tell us not only if there are outliers, but whether or not those outliers have influence. And we'll look through some of the other examples that are available to us as well. So we're using the Davis data set that is available to us through John Fox's website, our textbook in class. I'm going to analyze, go to regression and linear. We've done this several times in other videos. We're going to use reported weight as our outcome measure and measured weight as our independent variable. Female is a code of 0, 1. It's a dummy category variable. 1 is female, 0 is male. We've seen that in our last video. And then we have an interaction effect of measured weight by our code of 0, 1. And we'll put that into our model as well. There's a lot of statistics we could run. We're going to focus in on the save option under this dialog box. Previously, we've seen some of the predicted values and residuals. This time we're going to select studentized residuals. We're going to think of them as t. So as we get larger and larger t values, we would tend to reject our null. So in this case, when we get larger and larger t values, maybe size 2 or greater, we're going to be suspicious of those outliers. Here, we can also look at leverage points that we looked at in class. That's hat values and Cook's D. We'll just start with that. That's enough to start with. We'll click continue. Plus, it'll give us a range of values. I'll show you how we can shortcut some of what we're looking for as well. And we click OK. Our analysis comes out. We have our model. We just did one model. We didn't do any other blocking. We have a regression with 0.94 R and R squared of almost 0.9. It's a relatively large R squared value. It is significant. And we can see all three predictors are significant. So the main effect of measured weight is significant. The main effect of female is significant. And the main effect of the interaction is significant. I'll also refer you both to our textbook and to our course lecture notes for some of the visualizations of these. We did this in class as well. I'll come back to this shortcut in a moment. First, I can see that I have our standardized, studentized residuals. We could sort this if I wanted to. I'll sort by descending. You know, these values are relatively large. They're not too surprising, but these are the border most positive values. And then if we sort by ascending, we have some missing data in our data set. But we can see that a negative 11 value is pretty large and is certainly an outlier. When I say we have missing data, we can just look at reported weight. We see that some people did not give us their reported weight, so they're not included in the analysis. We can do the same thing with Cook's D. We're going to be looking for some large values here. We can already see one. We have a value of 85, which is pretty large. And it goes down all the way to 0. So that also corresponds with our studentized values. Sometimes that will happen. You know, our two largest Cook's D values are also our two largest standardized studentized values. So we might be most suspicious of these values. And then we can also look at our leverage points. We can see those should go down to 0 as well, towards 0. And our largest leverage point, thresholds here are a little different. You know, for our leverage points, that's actually a really large leverage point. It's in class we talk about how to look at the cut scores for those. But one of the things that I tend to do is I simply start with rank ordering. And in this case, it's really simple. The rank ordering of all three of those values all put this value here, this first top value, as a problem. And there's a couple things we mentioned in class that we could do. First, we could remove that value. That's an outlier somehow. We could first kind of graph. We'll do a little picture. I said we'll rely on some of the pictures from class, but I'll just do a little graph here, simple graph of our outcome of, we believe we used reported weight as our outcome, and we could use measured weight here, our axis, and get a little plot. We can certainly see well over here there's one outlier. Everything else, this is kind of an outlier, but it's right on our regression line. If I go in here and we give ourselves a linear line, we can see that this line down here is probably having a large impact on what's going on in this model. So let's temporarily remove it. Let's go to our data. And could create a variable for a filter. We'll just create that. Everything else is 1. Everything else is missing. I will transform this. This time I'll transform, just since it's not that meaningful here, I'll transform it into the same variable. We will take that new variable, old and new value. If it is 1, we'll consider it to be a 0. If it was system missing, if it was 1, if you don't hit add, it doesn't add into your model. And then if it was system missing, which is the case for all other variables, we're going to create a 1. So we're going to flip this around a little bit. Click OK. And I've just created a simple code that we can use to remove the effects of if we want to filter. You can make this as complicated as you want. I could have just deleted that variable, done it several other ways. Just thought it would be interesting to see it done this way. We can select a variable, click OK, and it should remove. Now we see that slash mark for that filter variable, which is coded 0. It's slashed that out. We will not include that in our analysis or in our plots. So now when I plot this again, the same exact plot, except removing that one case, and we can see there's really that there was a lot of influence on that R squared. That one point wasn't just an outlier. It was truly leverage points. Like a lever, it's pulling down our R squared line. When we go look here, we see our R squared has gone from 0.69, almost 0.7, to 0.97. Everything's on this line. And this outlier, it's not an outlier at all. It's right on that line. I mean, it's an outlier. It's further away on the x-axis than most things, and the y-axis, but it's in the same direction. It's right off that line. That is not the most problematic the problematic case that you would see. There are some other interesting things we could look at. We do our linear model here. We'll run the same linear model. We'll also ask for collinearity diagnostics. Continue. And under save, we won't do Mahalanobis distances. They're very similar in some ways to Cook's D. I mean, not calculation-wise, but we're just not going to do those right now. We will, I mean, in class we talked a little bit about them, and that those are, give us a large distance. A large distance is problematic, just like a large Cook's D is problematic. You know, Cook's D in many ways is an average coefficient. So a large Cook's D indicates that our case that we're computing, it changes the coefficients substantially. We could also then directly look at coefficients. So we could look at this DF beta value and just add that in. And this is going to be the beta value if it's changed individually based on having that outlier in our model. I'll click continue. Now first I'm running it without our outlier in the model. I'll click OK for all the values. And we see that we have replicated some of those Levine's too. Now it doesn't have our first outlier anymore. Things don't look too bad. And then DB1 underscore 1 through DFB, all these three, 0 through 3. This is intercept. This is our coefficient 1, coefficient 2, coefficient 3. So when we look in our analysis, this is related to coefficient, our intercept 0, our coefficient 1, coefficient 2, and coefficient 3. And we could look at these to see if they're abnormal in size. We could also run this analysis removing our filtered variable using everything in our analysis. So I'll reanalyze, do the regression a second time, and we should get our original values, which is let me go, yep, that looks like it's correct. And we can see Cook's again is a problem, and so is our standard studentized residual. And we can see that these values, some of them are relatively large. In a way, these DFB, these DF beta intercept, and these DFB coefficients, highlighted, it tells us this one's for measured weight, free male, and the interaction. These are very much akin to a broken out version of Cook's D. So this is like an aggregate form, and this is similar to breaking them out. Last thing to look at for this short video is we have residual statistics. When you go down the options in your regression for different residuals and things you could calculate, these are many of those options. We have Mahalanobis distance, even though we didn't ask for it. These are just the aggregate statistics for it. So it gives us the average score, which is very helpful, especially when we're thinking about Cook's D. You can use this average score, and you can multiply it by 2 or whatever value you want as your rule of thumb. But we can use this average score to see if there's a problem. We can use this average score for our, where's our studentized residuals here? We can see that we have a big outlier at a -11 when the average score is almost 0. And we have our leverage points, which again, we can do the same kind of thing with leverage points. We can see the average is 0.01, almost 0.016. So 0.709 is relatively large magnitude. But for any of these values, you could look at the minimum, maximum, and average scores and standard deviation and make determinations. You could just look at these first and say, well, the Cook's value, most of them are around 0.4, and one of them is 85. That's very noticeable. For our centered leverage points, most of them are around 0.016. Even the standard deviation is very close. 0.7 is huge relative to those. So that kind of red flags those as those maximum values there. And same thing with the studentized values. We see a maximum of -11 and a minimum of -11, maximum of 3. So absolute value, we have almost a 12 here. That is really large relative to our means and our standard deviations. Standard deviations here, we go 2 standard deviations out. That 3 is a little bit concerning, but when we investigate, we're probably not too worried about it. So there's a couple things to note. Just because we're investigating doesn't mean we're removing data from our data set. However, as I noted in class, there's a difference between whether we have a real problem or a perceived problem. The real problem in this case is that someone incorrectly entered in data. So that value should actually be 156 as opposed to 56. If you can trace that back through your actual, whether you have some measure of verification after the fact or whether you go through and see that someone typed something in incorrectly, then you could correct it. If not, you're not going to go in there correcting it that way. There's other ways potentially of examining that data or removing it, but it doesn't necessarily mean that this should be removed. If that's a real case, you need to consider that in your assessment of your model selection and what to do with the data.